Yes, I'm a postdoc at Monash, and I work with Ilya, which means that by induction, I don't use Phantom, and therefore I'm an imposter too. So I think I've been exposed here. But having okay, thanks. But but having heard Ilya's talk, I was inspired, and I thought it could be a nice idea to discuss some things and maybe do some brainstorming. And yeah, people normally, when people ask me here in this room, what do you work on? I'm like, I kind of feel a bit uncomfortable sometimes because I don't really have a good answer for that. Because sometimes it feels like everything, sometimes it feels nothing. And I guess you know what I mean. So initially I had some background in plant formation and like dust and stuff. And then I moved to doing some dynamics, general free body dynamics. And I think since I came to Monash, I kind of spent most of my time here in the high mass, high distant, high separation scales. But yeah, so I kind of always, sometimes I just don't feel belong anywhere. But then I kind of went to the Phantom workshop site and I saw this thing. And so this is like the topics we have in this workshop. And I kind of feel that, yeah, I think I can recognize some of the words here. And it seems like there's some significant overlap between what you're doing and what I think that I'm trying to do. And so I thought it's nice to maybe have some discussion on that. And yeah, but so I thought, yeah, that I didn't do anything with this page, but actually I just remember that, oh, sorry. So we'll just go back to smaller scales for now. We'll go back in time to kind of speak on planetary stuff. So I thought I didn't do SPH, but actually I was involved in a paper that kind of tried to do some SPH study. Not me, it was mainly Uri that did all the SPH work. So here in this case, we looked on Arrokoff, which is basically a Kuiper-belt object here in the solar system. And it's a bit weird because it has this large misalignment of 98 degrees with the spin axis and the orbital axis. And it looks weird. It looks like that. I think it's been yeah, it's been photographed by the New Horizons building. Telescope. And yeah, and we try to kind of to think how it forms, and I kind of did the dynamics the free body dynamics that allow it to form and collide. And when it served as the initial conditions for the SPH that was done in this study as well. And I think initially, yes, I think this should demonstrate that. I think if we try, so if I have initial conditions for different impact angles, we can do some SPH and simulations to see what's eventually with the spin period. And actually, it falls nice on the line of perfectly inelastic collisions. So we use some different SPH method developed by these people. I think it's called Milov-Koda, and it has some equation of state for solid bodies that maybe some of it can be implemented into Phantom, or maybe it has already been. So maybe you can update. Yeah. Okay. Yes. So maybe we can think of that too. And yeah, we kind of show that you can have different strength of materials and kind of get the rough idea, roughly the same structure. But if you kind of collide things which are all of high velocity impact, you're gonna get like squashed and kind of not getting the result. Okay, but this is nice. I mean, this is for already fully formed planetesimals. Maybe we can go a bit one step further and actually ask how to actually form planets or planetesimals. So that's my theorist view. I want to get from here to over there. So it needs to be fast enough, and it needs to grow in at least 12 orders of magnitude, which is quite a lot. So obviously different physics will play different parts. So I think, yeah, actually it could be even earlier if you look on HL tau. So we see giant planets kind of forming very, very early. So maybe it's even more challenging. So the first phase is easy. It's just basically sticking. So maybe once we have planetesimals, maybe we have some gravitational growth, but it could be too slow unless recently people have developed pebble accretion. Basically, you just accrete pebbles and not gas, which makes things easier. But how to actually do planetesimals? That's a bit hard, because here you have like many barriers. I think the radial drift that Salas mentioned, and fragmentation. And I think I also introduced, and I think also Stefan mentioned roughly aeolian erosion that kind of limits the size you can grow at, which is annoying. But still, how people think that it's formed. So I think there are like mainly two options. Either you have like a successive chaotic growth. Basically, maybe if some two bodies collide with a smaller velocity dispersion, with a smaller velocity, it can eventually grow, or just wait long enough until assuming stability does its magic and gravitationally form planetesimals. So I think that's the preferable theory currently. So it was true at least, yeah, so I think there's like a video I stole from somebody. So basically you have like a shearing box simulation, and eventually you wait long enough for the local dust to gas ratio will increase above unity, and then you kind of form these clumps which should be collapsing. So I think that was string instability, and it's really successful. But it has been done mainly for, how do I skip slide? Okay. It has been like done mainly for one size of dusts. And I think like very recently, I think these guys, they kind of show that if you actually use like multiple dust species, you could have some convergence issues, especially if you don't use one Stokes number, which has been discussed already, so I skip this. But if you have like a variety of Stokes numbers, you actually don't, it actually quite slow and it may actually not converge at all. And their conclusion was that, okay, we found this really big bug in our theory. We don't know how to fix it, but maybe if we can filter the size and the location of the pebbles, maybe it should still be fine. So I thought of that, and actually I realized that yeah, maybe this erosion thing it was a barrier, but maybe it could also be a solution. And yeah, so erosion is basically you take like a pile of dust and blow in on it, and it kind of falls apart very fast. And it's also depending on the relative velocity. So if you have like a larger pebble, it starts to get eroded. If it's smaller, it has a lower Stokes number, so it becomes more coupled to the gas, so it has lower velocity until eventually you have some kind of equilibrium place where you kind of stop eroding and you kind of stuck. So the idea is that every like location in the disk has its own critical Stokes number for which it's kind of stays. So I think it provides like a natural certification for the location of the disk. And I think if you maybe imply that, maybe it will actually help string stability to form, because each place has its own typical dust size. So I think maybe we'll try to do something about that while Stefan is here, hopefully. He's smiling, so it's all good. Yeah, the other thing is that maybe this is hard, this thing is hard. It's hard to do it like in every single system. Maybe I'm in a cluster and maybe I can do it like in one particular disk. And maybe I can just kind of eject decimals and kind of capture them. So I think, where is my graphic? Okay, pretend you have some Oumuamua here. They kind of, you capture them. Maybe some of them are getting ablated and kind of decrease in size, but maybe one is actually getting captured, which is large enough or far enough. And then it grows, so you can kind of import already fully grown decimals. So as a suggestion at some point that it could maybe help with the meter barrier to just kind of import stuff from other systems. And we actually can have many of them. We can have like millions of things that we can capture during the lifetime of a protoplanetary disk. But then we can have, and actually most of them actually captured quite close to the center, mainly because you need like a large density to capture them to lose their energy. But then, yeah, we had this issue. If you have like a solid body that penetrates a gaseous disk, you may have a significant ablation, and you also have some feedback on the disk. And we just said, yeah, it's fine. We have many numbers, so it should work out, because out of the million systems we have, maybe 90 of them gets ablated. Fine, we still have enough, but still, I think I would like to maybe look on some feedback from the disk and see what happens. So I just throwing some ideas to kind of maybe we can look on that. Yeah, I forgot to say, I'm just going to suggest various things I'm thinking of, and each idea is kind of has increased levels of craziness. So I think that's the second one already. I hope it's not too far-fetched. Yeah, so the idea is that maybe we can kind of look on captured things like close to the disk and try and kind of understand the feedback that we can get. So, okay, that's fine. So that was this part of the diagram. Maybe we can move a bit to the larger scale when we have like AGNs and star disruption and stuff like that. So I've been recently thinking more about that. So I think we know that we like also merging black holes. It's been a new field now. And you can have like, you can go to this review by Ilya and kind of review the various channels that you are going through. And at least the nuclear cluster channel is actually quite nice, because you also have like the cluster of stars or black holes, and you can also have like an AGN disk, because some galaxies are active, and I think there's some disks around them, and there are some similarities between AGN disks and protoplanetary disks. I think some people have discussed on that too. And I think it's a promising pathway to form black hole mergers over there. And it has been discussed a lot in the literature. And I think one of the key assumptions in this merger is that if you take like a black hole, it will just like migrate as a type 1 migration in a disk, because it have this 2 spiral arms and 2 torques that you can kind of move things around, which is fine. It was kind of imported in some sense from planetary science to AGN science, but I think there are some differences, because mainly the objects that are migrating are compact objects, and they should try to accrete, but it's an optically thick environment, so maybe they're also luminous. And whenever we have luminosity, I mean, recently there has been some discussion about thermal torques. Basically, it means that if you have an object in a disk and it can radiate its energy away, let's say if it's pebble accretion and you have some radiation, or if it's a black hole, then actually you can actually diffuse some of this heat in the disk, and you can have this kind of perturbations in the density that could affect your torques eventually. So so that adds to the total torques. So we have this potential thermal torques, and I think that the theory after these simulations have done and uncovered that it has been the analytic linear theory was developed by Frédéric Masset. I think he's the author of Fargo, and he has this theory for that. And yeah, so that was like a general discussion. And then after a while, these people came and said, "Oh, maybe we can try to simulate these effects in general disks, like numerically." I hope I'm allowed to show like results from grid codes here. But yeah, this is the results from grid codes. I think the geometry, the way it goes is we have like 3 different length scales. So we have like the co-rotation radius, which is the smallest usually. We have the scale height, which is the largest. And we also have this lambda, which is roughly the diffusion length. It's roughly somewhere in between. And it means that if you have some heat, it diffuses. Eventually, the diffusion time increases enough until the Keplerian shear takes it away. So you may have this kind of blob of hot material, which is also simulated here with like typical length scales. And because of this asymmetry, it's not really at 0, you have some asymmetry. The total torque is proportional to basically x over lambda here. And it's also like a new effect that only now has been addressed in AGN disks and or in general disks. And I think this is like the only paper that I'm aware of that have thought of this AGN stuff. Okay, great. I think I'm actually on time. Yeah, I'm happy. Yeah, okay. And I've kind of tried to look a bit more on that, and I kind of tried to kind of take the linear descriptions for the torques and kind of apply it for some AGN disk structure. And I tried to look on actually what happens to migration traps and stuff. And if you just look only on the, so that's like the separation and the normalized torque with some quantity. So if you have like only like gravitational torques, only type 1, so negative so dash is negative and solid is positive. So it means that formally you should have like a migration trap here. So you should trap black holes here, and then they maybe form a mini cluster and merge. But now if you have the thermal effects, it actually moves away. I think it should be here. So I mean, it kind of destroys all this. It could potentially destroy all this nice thermal torque structure, all this migration trap structure, mainly because it affects the overall torque. So I mean, I'm using some similarity calculations, which I mean, I think it's still like compatible with the linear theory, but I kind of recently ran into some dead end that basically I think in these areas some of the assumptions kind of break down. I have some nonlinearity, so I'm not really sure how to treat that in a better way. So maybe some people that like to do AGN disk could maybe discuss on that. And okay, one slide on a final idea, which is completely crazy, but fine. I think I have 2 more minutes. So yeah, in any case, also assumptions are interesting. And we know that at least in our galactic center, we have this supermassive black hole here. We know it's a supermassive black hole because we actually can resolve all these orbits here of these very massive stars. We don't really know how they form. So I wrote a paper with the Rosalba Perman that kind of tried to discuss what are the reasons to believe that there is some connection between the recent history of star disruption events in the galactic center and the formation of these young stars. So maybe they're related. And yeah, and basically there is that if you have a cloud and if a shock runs through it, it may compress it and reduce its Jeans mass. So maybe you will be able to form stars near the galactic center. I know it's crazy, but stars have been spotted, star formation sites have been spotted in galactic outflows. So maybe it's not that crazy. And yeah, and maybe we can kind of also think of that. So yeah, so I think that's like my journey from here to here. And yeah, if you want to chat with me, I'm here, and thank you for your time.
Does anyone have any questions for Evgeni? Sorry?
I just was wondering about the planetesimal capture scenario that you mentioned. What did you have in mind exactly? Like the planetesimal having a hydrodynamical interaction with the protoplanetary disks, or just a gravitational capture from planetesimal? So my point is, the planetesimal was formed around another star and it was then captured by the disk.
Yeah, so yeah, that's right. I think so. I think if you look on the plant formation, basically, eventually, as the gas dissipates, you are expected to eject like at least some Earth mass in solids, and some of them just go into the ISM maybe. But yeah, I think if you have like neighboring clusters or whatever, it can just kind of if you look on the Muamua, you know that you should expect like an encounter like once every 100 years or so. So if you take like and if you take like the typical atom of a disk, it's roughly like a few thousand maybe of one more sizes, and if you also include the mass function of planetesimal, it's larger for the smaller mass. So yeah, just kind of you stick a disk and maybe something stick on it. And
so instead of having like an interstellar object just crossing the solar system and never coming back, you would like the planetesimal to actually collide or go through the
because it's
gaseous disk.
It's very hard to collide with Jupiter because it's too small. But if you put a disk initially, it doesn't live that long, but the cross section is much larger for dissipation.
Sure. Okay.
With the gas, so you need like to have enough surface density to make the dissipation efficient enough. So I think because the velocity is very large, you just have like a round pressure regime. So if you lose enough energy, it can be bound. You can kind of calculate the for which density and location, which size would be bound after the first encounter.
Would your idea be like maybe in the early phase of star formation? Maybe like in the early phase of star formation, you say like maybe if you made a bunch of planetesimals and they're getting ejected by some disturbances, then they would get captured by other disks. Is that the idea?
Yeah. But the thing that is that we don't need to form it in every system isolation. We've seen that when you have like flybys and other things. I think we should just think of interaction between neighboring systems.
I have a question. On your slide about the thermal torques and your modified torques, I just wasn't entirely clear how you were calculating those. Were they just like the linear Lindblad torque plus the Massett thermal torque?
Yes, so I think the analytic theory for the thermal torque is actually in this paper. It's in 145 in this paper. Yes, you like to write long papers. So there's a formula for the thermal torque in this paper.
Yeah.
And for the total one, you just kind of add this thing together. Yeah, that's it. The total, just like the thermal and the gravitational one combined.
Right, and so the minimum is where the traps are.
Yeah,
is that
so
right?
it changes sign here because if you just put them on the green line, so here it's negative, so things move inward. Here it's positive because the pressure gradient can change sign. So that's positive, so you should have a trap here. But if you have some new formula for the torque, it may move a bit, it may not be there at all. It depends on this kind of very preliminary for me. Yeah, but also I'm not really sure that I can use this thing together, or maybe maybe the thermal torque it also affects the rotational one. I just ignore that for now because I don't know how to answer that.
Okay, thank you. Were there any other questions? Yeah.
I have a colleague that has been working on how this thermal torque impacts like the planetary migration. And my understanding is that at some point this thermal torque saturates and stops working after a certain, in protoplanetary disks, so no AGNs, it's about of a few lunar masses or something like that. Then the thermal torque saturates and it's not growing anymore and becomes insignificant at some point. I was wondering if you have a similar effect for AGNs.
I'm not sure. I'm just relying on kind of the analytics and this paper kind of simulate it numerically. So yeah, I'll be happy to hear about the saturation effects and maybe kind of explore the assumptions if they're valid or not for AGNs.
Okay. Thanks.
If there are no more questions, I'd like to thank Evgeni once again for the great talk.